Enzymes and how enzymes function to catalyze reactions. And I wanted to use this PowerPoint to talk about some of the factors that affect how well an enzyme functions. So we're going to go through 4 different factors. We're going to talk about how temperature affects enzymes, how pH affects enzymes, how salt can affect enzymes, and then we're going to talk about allosteric regulators, which are other molecules that can attach to the enzyme and change how it functions by turning it on or off. So let's start with the environmental stuff. This graph here shows how temperature affects enzymes. So we have enzyme activity on the y-axis and increasing temperature on the x-axis. You can see at a low temperature enzymes don't work very well. That's because everything is moving really slowly, so the substrate doesn't bind with the enzyme very frequently. As we increase temperature up into a point, we have increased enzyme activity. Molecules are moving faster as temperature increases, and the enzyme can catalyze more reactions as it binds to the substrate. You can see after a point, however, enzyme activity drastically decreases and the enzyme stops functioning. When the temperature gets too hot, the bonds that hold the enzyme together start to denature. The enzyme loses its 3-dimensional shape, meaning the active site is no longer going to fit the substrate. So that's why we have that decrease in enzyme activity at high temperatures. It's due to denaturation. Okay, so here we have a graph of pH with several different curves. Most enzymes work best at about a neutral pH, somewhere between 6 and 8. And that's what this orangey line is showing. At a low pH, meaning that it's too acidic, the enzyme doesn't work very well. And then at a high pH, again, the enzyme also does not work very well. At either ends of the pH spectrum, if it's too acidic or too basic, the enzyme is going to lose its 3-dimensional shape, it's going to denature, the bonds are going to break, and it's not going to be able to join with the substrate to catalyze the reaction. However, right in the mid-range at about a neutral pH, the enzyme works great, and we have the most enzymatic activity. Now, not all enzymes fall into the 6 to 8 normal ideal pH range. You can see here we have pepsin, which is actually a stomach enzyme, and your stomach is very acidic. So this enzyme is programmed to work at a very acidic pH, and it has its peak activity, at between 1 and 2, which is extremely acidic. However, if it gets to more of a normal pH range, then it denatures and it no longer functions. So pH is a little bit different as compared to temperature. There's still an ideal range, but there can be some variation in that ideal range. Okay, I don't have a graph for salt, but the take-home message with salt is very similar. If the environment becomes too salty or not salty enough, depending on the enzyme is going to denature, we're going to lose the 3-dimensional shape, and it's no longer going to function and be able to bind with the substrate to speed up the reaction. In your body, you have allosteric regulators which affect how well enzymes work. And the term allosteric means different structure. And allosteric regulators are just molecules that bind to the enzyme at a site other than the active site and cause the active site to change shape. It can either turn an enzyme on or it can turn an enzyme off, depending on the situation. And it's reversible too. The allosteric regulator can release from the enzyme, and the enzyme can go back to its normal state. And this is used to regulate enzymes. It doesn't make a whole lot of sense for the body to create a lot of product if it's not going to use it immediately. There are some enzymes that need to be on and functioning all the time, but there are also enzymes that are only used every once in a while. So this is one way that we could turn an enzyme on or off depending on the body's needs. Okay, so this is one example called allosteric activation, where the allosteric regulator turns the enzyme on. So normally the enzyme is off. You can see here's the active site. It's circular in shape. It's not going to bind the square substrate. Here's the allosteric activator. It looks sort of like a horseshoe, and it has a different area on the enzyme where it can bind called the allosteric site. Signals are going to be given off to the enzyme, and it's going to tell the allosteric activator to bind to the enzyme. When that happens, the active site changes shape, and then the substrate can bind, and now we have the enzyme on. The enzyme will remain on as long as the allosteric activator is bound in the allosteric site. There are other enzymes that are created in the on position, and an allosteric inhibitor can turn them off. So here the enzyme is functioning normally. The active site is the correct shape to bind to the substrate. Here is our allosteric inhibitor, and when it binds, this again changes the shape of the active site, this time making it so the substrate will not bind. In both situations, the active site changes shape. In this case, with allosteric inhibition, it's inhibiting the substrate from binding to the active site and basically turning the enzyme off. It will remain in this off position as long as the allosteric inhibitor is in the allosteric site. There's a special type of allosteric inhibition called feedback inhibition, and in feedback inhibition, instead of another random molecule being the allosteric inhibitor, the product acts as the allosteric inhibitor. Okay, so here we have the substrate, and it's going to bind to the enzyme to create the product, and it's going to go all the way through this pathway, creating this end product. And as the end product starts to build up, the enzyme is creating end product faster than it can use it. So one of these end product molecules comes along and binds to the enzyme and turns it off. So here, this was the active form, and now the active site has changed, and it's no longer going to bind the substrate, and it's going to stay in the off position. The cell is going to start to utilize these end products that are available, and it's going to use them all up until the only end product left is the one that's attached to the enzyme. The cell is going to take that end product because it needs it for another reaction. The enzyme is automatically going to turn back on and start to create more end product. So feedback inhibition allows for very quick changes in turning the enzyme on or off, since the end product is already there pretty much next to the enzyme.